Hi everyone, this is Becky, and in this video we're going to take a closer look at the reaction coordinate diagrams that we started drawing in class the other day. So the goals of this video are for you to be able to interpret reaction coordinate diagrams that are given to you, to be able to use reaction coordinate diagrams to identify reactions as endothermic and exothermic, and then to be able to draw the correct reaction coordinate diagram for a given reaction. So whether that given reaction is exothermic or endothermic, being able to draw the appropriate diagram for that. So let's do a little bit of a review of what we talked about in class. So let's consider a reaction where I have A2 plus B2 reacting to form 2AB. So in class, we talked about this, and in particular, what needs to happen in order for this reaction to occur. So if I have my A2 molecule and I have my B2 molecule, which I'm going to draw in blue, and then I'm forming two molecules of A and B where I have A bonded to B, like so. We talked about this idea of collision theory, where in order for this reaction to occur, A2 and B2 have to collide, and they have to collide in the right orientation and with enough energy for the reaction to occur. So we can picture that as kind of happening this way, where we have a collision between A2 and B2, where we're kind of colliding like that. And then where we're kind of in the middle, so these two collide. When they collide, we start breaking these bonds, or making some bonds that I'm drawing in black and breaking some bonds that I'm drawing in green. And then we get from this, our reactants, to our products through this kind of intermediate step where we're breaking bonds and making bonds. Right, and so we looked at this in terms of looking at energy piece, the energy piece, where we drew this diagram, right, where if we put potential energy over here on this graph, and just a general energy term, and we look at reaction progress here on the y-axis, or on the x-axis, sorry, excuse me, and then we look at, okay, so we have reactants that contain some amount of potential energy, and we have products that contain some amount of potential energy. And then in order to get from reactants to products, right, we have to collide. We have to transition through that intermediate or that transition state step. So here would kind of be this transition state step here. This part here corresponds to the energy of these, and then the energy of the products would be corresponding over here to this diagram here, right? So this diagram is called a reaction coordinate diagram, where we're kind of mapping out the energy involved in this species in changing from reactants to products, okay? So reaction coordinate diagrams can take a couple of different forms, as you can see here. So sometimes it turns out that the reactants have a lower potential energy than the products, and sometimes they have a higher potential energy than products. But a couple of things I want to draw your attention to. Number one, there is always this hill. And this hill is actually so important that it has a special name. And the name that we give to this hill, so in fact, energy, the difference between the energy of the reactants and the energy of the top of the hill, is called the activation energy, or the E sub A, which is the activation energy. And that activation energy is the energy that's required to form the transition state. And that transition state, remember, is that kind of in between where you have those bonds breaking and bonds making, right? So what's happening here, you have your transition state, which is super unstable, super high energy. And so the amount of energy that's required to form the transition state is equal to the activation energy of the reaction. All reactions have an activation energy, right? So if in this case, the activation energy would be here from the energy of the reactants to the products. This delta H value here represents the energy of the reaction. So the heat of the reaction, remember delta H is always going to be products minus reactants. So in this case, if we look at this particular reaction over here, reaction A, notice that in order to go from reactants to products, we had to gain energy. Products have more energy than reactants. So in this case, the system is absorbing energy If the system is absorbing energy, that's going to be an endothermic process. Endo, energy coming in, entering, right? So it's absorbing energy, absorbing heat from the surroundings, which means that the surroundings or the beaker is going to get colder, right? And whereas here, if we look at this one over here, if we look at B, the reactants, the products have less energy than the reactants, which means that the system lost energy, which means this reaction was exothermic, in that the system is releasing energy to the surroundings, which means that the beaker is getting warmer. Okay, so a couple of things that I want you to keep in mind. Look at reaction coordinate diagrams. Number one, when we have this diagram, remember that this x-axis is reaction progress. It's not time. Okay. This is not time. These diagrams give no information about how long in this reaction or how fast this reaction occurs. It doesn't tell you anything about whether this reaction is happening over the course of millions of years or the course of a couple of milliseconds. All it tells you is the difference in energy between the reactants and products and how much energy it takes to form their transition state. Now, as we'll see when we think about the factors that affect reaction rates, we can get a little bit of information about the relative rate of a reaction from this diagram, but really it doesn't tell us anything about whether the reaction is fast or slow. Okay? All of the reactions, and remember that all of them, no matter how I'm drawing them, from big to small, have a hill. There is always an activation energy. Always, 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 no matter what. There's always an activation energy for a reaction. So things never go in terms of energy directly from reactants to products. We're always going to have to go up some sort of hill. The hill can be really small. The hill can be stupidly huge, but there's always going to be a hill. Right? Always going to be a hill when the reaction occurs. So in thinking about reaction coordinate diagrams and applying reaction coordinate diagrams to reactions, think about this particular question. Right? So I have a small amount of solution A mixed with a small amount of solution B in a test tube. A pale yellow solid, which is substance C, is forming, and the temperature of the test tube is decreasing. So given that, write a chemical equation that describes the reaction that's occurring, and then draw an appropriate reaction coordinate diagram for this reaction of A and B making C. Okay, draw that in your notes and bring that with you to class tomorrow, and we'll go over it in class. Have a great day.